I was recently presented with a task to perform with a really short deadline that was seemingly impossible. I wanted to document how I pursued a solution to this sort of issue. So let's just go ahead and jump right in. Uh, in short, really simple on the face of it, and that project team provides you with a spreadsheet full of different exceedance data for certain chemical analytes. Those analytes are broken up into groups and separate depth intervals. Each one needs to be used to create an interpolated data set so we can make this series of figures, and then those figures are that's the deliverable. um, not a huge deal, except that just the sheer amount of data, um, that when you think about it, when broken out, one data delivery for one area results in a lot of maps. So this is a fictitious area A. Um, Row 3 right here lists every one of the analytes that we want to model. There's 24 of them. And for within each analyte group, we have 4 distinct depth intervals, and these are reported in feet. 0 to 0.17 feet, 1.7 to 0.5, 0.5 to 1, and 1 to 2. So that's 96 total data sets and corresponding maps. So how do we go about doing this? Well, essentially what you would need to do if you were doing this manually is you would have to physically make all of these definition queries and run the data. It's a cumbersome task, right? So what I did was I used a Python script that I basically, the short of it is that this Python script went through and grabbed every unique case of area, analyte, and depth group, and pumped that into a dictionary and created a case-specific definition query that you can then use to just automate the creation of these data sets. So let's take, for example, just arsenic within one specific area. The script has gone through and it has it's created a data set that's specific for this area, with this analyte at this depth interval. It then repeats that for each depth interval. Here's 0.17 to 0.5 and so forth and so on. The nomenclature here is like this in order to accommodate just naming conventions within ArcMap. One other important thing to note is that the data set right here, the actual analytical data, was migrated into into an ArcInfo table inside of the geodatabase. I'm going to point out later why we want to preserve this, but this data table serves as the source for every one of these corresponding data sets that exist inside of the geodatabase. Another thing that's important to note is that the database really only included the exceedances, that is, these areas in red for this area for arsenic at this depth interval. It's not really ideal to run the interpolation just on the exceedance data, because if we were to do that, it would actually there'd be no values that would constrain this interpolated plume for arsenic at this depth. It would just happily interpolate out everywhere. I'm using inverse distance weighted here because I just needed a really simple, cartographically pleasing raster data set. So in addition to creating feature classes for the exceedances, we also had to create kind of a dummy file. The dummy file consists of sample locations that were non-detects, that is, they didn't exceed some threshold criteria, and we also needed to add dummy points to the perimeter of the area of interest. And I'll show you why that's really important, and you can see their effect right here. When we interpolate based on values, these values are set to 0 where we have these white points. It helps to constrain the plume so that it just doesn't grow outside of the bounds of what we're interested in. And that data set was done really for each area. All that we did was I had one base dummy data set for each area. So for this particular area right here, it actually just made a blank copy of all the dummy points along with really every point in that area. It creates a copy of that for each represented case that we had. So if in this case here, there were 4 depth intervals for arsenic in this area, this OU1C area, it copied 4 blank data sets to there. Again, by blank here, what I mean is the result values were just all set to 0. And then later on, when we run the interpolation, those values are updated with the joined fields for the corresponding data set, i.e. the red data set. Okay, so there's that. The other really important reason to create the other important reason for leaving the analytical data or migrating the analytical data into the geodatabase is because it can then later be used to create the labels for this. So there's this label expression that we've built into the feature class, and it's dynamic in that it knows to go through the analytical data table and create a query and label the parameters of the query for starts with the group, the depth interval, and the exceedance values. These are all important variables inside of this label expression that can be used to create the labels, which are shown right here. Okay, so this just simply is what it is. You can go through and I built a label expression that does all of this formatting within the label text itself. And so this is really the workflow that I use to create essentially 500 figures in a very short period of time.